I want us to look at some very special logs, some really important logs. Of course, where I always start with logarithms is just the definition. Let me remind you that if I say y equals log base b of x, that's the same thing as saying that the log is the exponent, so b is the base raised to the exponent y to get x. And I want us to talk about some very, very special logarithms. The first one is if it's in base 10. If we have a base 10, that's called the common logarithm, and it's so common that we actually even drop the b there. So we don't even have to write the b when the b is 10. We just write log of x. And we understand, we've all agreed, all the mathematicians and math students in the world got together one night and said, okay guys, promise, if you see log of x, there's an invisible base 10 there. So base 10 is the common log. And the graph of that, it's the inverse of the exponential function, which means that it kind of has this very, very steep incline, then slowly, gradually tapers off, and then gets bigger and bigger and bigger. This gets larger and larger without bound, but very slowly. And there's a vertical asymptote on the negative y-axis here, and that's the graph of the common log. Now, that's not to be confused with the special base e. Remember that special number that's named after Euler? Well, that's called the natural log because it appears so often in nature. So we call it the natural log. And to not confuse it with the common log, we write ln for basically natural log. The n is natural. So ln x is a very fancy way or shorthand way of writing log base special number e of x. If there's log with nothing there, that means base 10. If it's ln, or natural log, x, that means base e. And if you look at the graph of that function, again, it's the inverse function of the exponential. The exponential function, remember, looks like that. So if we reflect along the y equals x line, whoop, you see that the blue perfectly matches up with the red here. And you can see that in some sense it's a little bit less steep than this one because the 10 is actually larger than e. Remember, e is around 2.71 stuff. So this is a little bit more gradual in its growth, and here this is much more dramatic, and that's just the way these functions are. Now, focusing on the exponential function for a second, I want us to take a look at some kind of fun little facts, which, we already kind of know. These are special cases. So the natural log of 1 equals 0. And why? Well, because e to the 0 power equals 1. Anything to the 0 equals 1. Let's take a look at the natural log of e. Well, there's an invisible base e there, so e to what exponent equals e? Well, e to the first, and so therefore the natural log of e is 1, the first power. Natural log of e to the x equals x, and that's the exact same property that we saw earlier. This is log base e of e to the x, so it's e to what power will equal e to the x? Well, the power has to be x. And then finally, this is the hard one, e to the natural log of x equals x. And why? Because I'm raising e to an exponent. And that is precisely the exponent I have to raise e to in order to have the answer be x. And so therefore it equals x. Phew, really, really tricky. Let's see if we can apply these things to actually find certain values. Okay, how about natural log of e cubed? Well, the natural log of e cubed, that's e to what power equals e cubed? Well, it's e to the third, using this property right here. So this answer is 3. Should I write that in? What do you say? In fact, I'm going to have the staff here tell me. Should I write it in? Yeah, they want me to write it in. See? So this equals 3. Great. Let's do another one. How about log of 10? Well, there's nothing written underneath there, and it's not the natural log. Remember what that is? That's the common log. So there's an invisible 10 there. So that means log base 10 of 10. Well, let's think about that. 10 to what power equals 10? Well, 10 to the first power. So this must equal 1, because 10 to the first equals 10. How about this one? Now, this one's a little tricky. Log of 0.01. Well, here, the first thing I have to do is do a little calculation, because I don't know what that is. That seems scary. But I know that's actually a power of 10. And remember, log with nothing there means there's an invisible 10 there. And this is 10 to what power? Well, negative 1, negative 2, so I'm going to say negative 2 power. So what's the power I have to raise 10 to in order for it to be 10 to the negative 2? Well, the answer is negative 2. And so the answer to this is negative 2. Kind of fun, isn't it? That the log of a tiny number is actually answer negative. And that makes sense because 10 to a negative power is something that's small. Awesome. And then finally, what about e to the natural log of 7? This is the one that's so tricky. Remember, natural log means base e, so this is e to an exponent. And it is the exponent that I have to raise e to in order to have it equal 7. So what does the whole thing equal? It equals 7. So tricky. If you understand this and it makes sense to you, you are so much better than I was because it took me forever. But thinking about logs, and in particular the special cases of the natural log, which is base e, and the common log, which is base 10, are two logarithms that will follow us for a long, long time. And it turns out they'll have great, great benefits, and we'll seek dividends by just understanding them as best as we can. I'll see you soon.